Good afternoon. I'm going to talk today about the effect of shear slip on fault permeability in Shale Reservoir rocks. And even though I'm now at Texas A&M, I just want to emphasize that this work was done while I was still with the geomechanics group with Mark Zoback and Kohli at Stanford. And so we will see those results from that experimental study. So the motivation for the study is to understand the stimulation of shale gas reservoirs. And this slide shows the importance of slow slip on pre-existing faults and fractures. The shear deformation that is associated with those slowly slipping faults is expected to increase the aperture from a small open aperture pre-slip to a much larger open aperture afterwards. And additionally, it is expected to create a network of multiple permeable planes that are surrounding the induced hydraulic fractures. And so that network basically enhances the overall permeability. That being said, we still don't really know how that stimulation works during hydraulic fracturing and how exactly the shear slip affects the fault permeability. So this slide is on two data sets from the Barnett Shale, and it shows the, Mark Zoback actually nicely introduced the left part of the figure already, and it shows here that in addition to microseismic events, long period, long duration events can occur as well. So here we have these two data sets from the Barnett Shale. On the left, we have data from 5 wells. On the right, data from 2 wells. And the circles are the microseismic events with the size being or showing the magnitude. Now, Zoback and Das interpreted or found that there are these slowly slipping events in addition to microseismic events occurring where those microseismic events are absent, basically here and here. So they can't really be detected with microseismic surveys, but they indicate slowly slipping faults. And as Mark mentioned earlier in his talk, you can actually see that these long LPLD or long period, long duration events, that those follow the same trend of the major fracture that was interpreted here in well C. So the bottom line of the slide is basically that there is evidence of aseismic slip on large faults during reservoir stimulation. There are several experimental studies out that try to relate the fault permeability to shear displacement. And here's one example on an intact rock. Li and Cho tested sheared joints in a granite, basically with a porosity close to 0%. They created tensile fractures in that intact granite block and then sheared it in a shear testing device. They used water as a pore fluid and measured permeability from flow rate measurements. And on the left, you can see the results. They plotted the fracture permeability as a function of the shear displacement for 3 different normal stresses. So you can observe that the fault permeability increases for all 3 different cases, with the permeability being the largest under the lowest normal stress as expected. Now, a different example is shown here, which is not on an intact rock, but on a gouge. So these authors, Okazaki et al., published in 2013 some work on Antigorite Serpentinite gouges. And they performed friction experiments and permeability experiments in a triaxial gas apparatus in 3 different directions. So they measured permeability in the slip direction, and then normal to the slip direction, but still along that fault plane, and then normal to the fault, which means basically across the fault. And on the right, you can see the permeability as well as the gouge thickness plotted versus the axial displacement, which can be converted into shear displacement. And you can see in this case that for all 3 different directions, the permeability decreases with increasing shear displacement or axial displacement. And for the measurements that are across the fault, the permeability decrease is actually the largest. So the bottom line is there are studies out on intact rocks, on gouges, on sandstones, granite, and other materials. Some show an increase in permeability, others show a decrease, but there's not really a study out yet on an intact shale rock, and those are the rocks that we really want to look at and consider when we try to understand the stimulation of shale gas reservoirs, and also when we're looking at CO2 storage. So our approach here is that we study the effect of shear slip in shales, in intact shale rocks, on the permeability for smooth and rough surfaces. And I will come back to that later, what I mean by that. And we are going to do that by performing shear experiments combined with permeability experiments in a triaxial apparatus. And then we will measure some fault roughness measurements before and after shear in order to compare those topographies. So here is just a little bit of information on the sample dimension and the test setup. We work with a cylindrical rock sample that's 2 inches in height and 1 inch in diameter. And the fault plane is approximately 30 degrees to the core axis. And we drill little holes in each sample half so that the pore fluid can actually access the fault plane. And we tested 2 different types of samples. The first type is a Sawcut. So we created a Sawcut at 30 degrees to the core axis in the rock. And the second sample type is a natural fault. So that sample was naturally broken in a previously performed shear test. And both of these have a very similar setup in the apparatus. The samples are sandwiched between the core holders. We have some membranes in between, confining pressure is applied, and the axial load that is applied induces that shear slip on the fault surface. And axial displacement transducers measure the axial displacement. The samples that we tested are from the Haynesville Shale Reservoir from a depth of 11,400 feet. And you can see the mineralogy up here in this table. So the Haynesville is mostly composed of calcite, 52%. It includes about 22% clay and 16% quartz. And at the bottom of the slide, you can see the 2 different types of samples that we used. On the left, the Sawcut sample, the top half and the bottom half. And on the right, you can see that natural fault that was developed in a shear test that was previously performed by a previous student in the group. And I indicated here where those little boreholes are that we drilled so that the pore fluid can access this fault surface. And I highlighted the top parts because these are the sample halves that we are actually looking at here in this talk that I'm going to present you the results for. So the test procedures for both sample types are similar but different in a little bit, so I'm going to just explain that. If we look at this sketch, which is not to scale, with axial displacement on the y-axis and time on the x-axis, the red lines are basically the permeability measurements, and in black we indicate where we did loading or unloading. So in both cases we start with a pre-shear permeability measurement, so before we actually induce any shear on that fault surface. And then we load the sample with a rate of 1 micrometer per second until we reach 1 millimeter. And then you can see the subsequent steps up to a total axial displacement of 4 millimeter. Well, the Sawcut sample we performed first, and we actually noticed that most of that permeability change is occurring early on at low axial displacements. So that's why we adjusted our setup a little bit for the natural fault and added increments. We basically went in 1/4 millimeter steps to improve our resolution at the early on part of the test. And the equation down here just shows how we got the permeability in the experiments. We basically assigned a constant inflow rate and a constant outflow rate and then measured the pressure differential on that fault surface, but because the length of the flow path is unknown, basically between those two holes, and also the aperture, and therefore the area of the flow is unknown, we are looking here at relative permeability, so we are normalizing the permeability to the pre-shear measurement. This slide shows the friction and permeability results for the Sawcut sample. We're looking here in blue at the coefficient of friction versus shear displacement, and in red the dots are the permeability measurements. So you can see that the Sawcut results indicate a stable sliding behavior. Initially the frictional strength rises rapidly, and then it approaches a constant value after about 0.35 millimeters, and then the frictional strength converts into a linear strain hardening behavior. The coefficient of friction ranges between 0.55 and 0.61, and you can see these little drops that's happening whenever we stop the loading in order to perform the permeability measurements, but the coefficient of friction quickly recovers and continues on that same trend it has gone on at previously. Now, we did 5 measurements, 5 permeability measurements in total here, 1 pre-shear measurement and then 4 subsequent measures. And you can see that the permeability, the fault permeability along the fault plane for the Sawcut sample decreases significantly. It decreases by 2.5 orders of magnitude within the first millimeter, and it continues to decrease. Now, just to mention the test conditions, we used a confining pressure of 15 MPa, pore fluid pressure of 2 MPa, argon is the pore fluid, and pretty much room temperature. Now, on the next slide, I'm going to show you the results for the natural fault sample. And you can also see here mostly stable sliding behavior, but with some small stick-slip events. The coefficient of friction also rises quickly initially, and then converts into a more linear behavior. And the coefficient of friction ranges between 0.6 and 0.74. The permeability also decreases, not as much as in the Sawcut sample though, only about 1.5 orders of magnitude within the first millimeter. Now these are the roughness measurements. So we used a 3D laser scanner, and this is the Sawcut sample before and after slip. So there's only a small relief of about 1 millimeter on the sample, with the low point of course being here in the drilled borehole. The small features that you see here were actually induced by the roughening surface after the Sawcut sample. So there's not much change really during the shearing process, only that some of the higher topography parts get abraded and we see a little bit more of a striation. Now for the natural fault sample, we have a lot more topography. We start out with 8 millimeters, and after shear we are only looking at 7 millimeters, so a whole millimeter on average was abraded. And you can see that the whole topography is a little bit more smoothly looking, and it's actually hard to find the borehole at this point. So coming back to this initial slide, how does really the shearing affect the permeability? Well, I've shown you results on a planar surface and on a surface that has some curvature and more roughness, but in reality, we really look at faults that are much more complicated. They might stick slip, they might have a damage zone, so it is not as simple. And we are basically replicating here a sample with a very small damage zone where we are mostly focusing on that low permeability core. And Mark introduced this figure. I don't have the time now to go into detail, but I just want to say that we hypothesize for these low clay contents, we expect a large damage zone, whereas a small damage zone for higher clay contents. And so in conclusion, the surface roughness significantly affects the flow behavior along fractures and faults, and the fault permeability reduction is much smaller for a rougher surface than for a smoother surface. And so I leave this up. I would just like to thank people for support, for using the laser profilometer, and for providing the course. Thank you.